Hello and welcome to Monochemistry. Today we're going to look at the concept of strong and weak acids and bases. And just to show you a few pictures here, these are from my lab, our lab here at New Germany Rural High School. We've got some hydrochloric acid here. We've got some sodium hydroxide here. Got some vinegar, and we've got some laundry detergent. Strong, strong, weak, weak. But how do we know? How do we figure that out? We're going to learn about that in this lesson, but also we're going to learn, you folks are going to learn the names and chemical formulas of the strong acids and bases so that you have them. There's unfortunately something you do have to memorize so that you know them, and we'll go from there. So let's start right away with the strong acids. Okay, so this is a picture taken out of the Chang chemistry textbook. So if you're in AP chemistry, then you have this. It's on page 668. If not, that's fine too. You see it right here in front of you. The ones labeled under strong acids, which include all the way from perchloric acid all the way down to hydronium ion. Those are the strong acids. So there's only 1, 2, 3, 4, 5, 6. There's 7. There's 7 strong acids. Okay? You need to write those down. The strong acids need to be written down and memorized. You need to know those. Okay? Might as well move on to the strong bases. The strong bases are hydroxides of group 1 and 2. More specifically, the ones in this list. The other ones don't technically work out, but these ones do. Okay, so you can see the strong bases. Notice that all of the strong bases fit under the Arrhenius model of bases. Okay, all of these strong bases fit under that model. But how do people tell the difference? How do we know these are strong and the other ones are weak? How do we know those other acids are strong and the other ones are weak? That's what we're going to look at now. Oh, I know. We could go in the lab and we could test to see which ones are strong and weak. Well, you can't use my hand to do that. All acids and bases are considered to be corrosive. Obviously, the stronger acids and bases are more corrosive than the weaker acids and bases. Here we have a couple of pictures of people who tested their acid and base strength in the lab. No, I'm just kidding. These were accidents, hopefully, not somebody who actually tested. This picture here is a picture of a sodium hydroxide burn, which is a strong base. And over here we have a nitric acid burn. Okay, neither one of those is something that I ever want any of you to experience. So obviously there's another way. There's a different way that we can do, other than going in the lab and dropping things on our skin or something else to test how strong they are. There's another way to test it, and that's what we're going to learn about now. We're going to learn about equilibrium constants of acids and bases. Now take a look at this picture. This picture here is a very good representation of what happens with strong acids and bases. Okay, so all acids and bases essentially are dissolved in water. A strong acid will dissociate in this manner. Notice we start off with the acid HA. We add it to water, and we get these two things. Remember, H3O plus and H plus are interchangeable, but notice this completely breaks apart into this and this, the H plus and the A minus. 100%. And the base would be much the same. The base would split apart into those two things, and it would be close to 100% dissociation. So the real definition of a strong acid and a strong base is as follows. A strong acid and base will dissociate nearly 100% to form ions. Right? Acids and bases that are considered strong do that. 100% or slightly less than 100%, but nearly 100% for every single one of those strong acids and strong bases that we just looked at. Now, here's what we have down here. It's called an equilibrium constant. This is something we'll learn more about when we talk about equilibrium, but let's just take a look at this. This is Ka. This stands for equilibrium constant of an acid. This is Kb, equilibrium constant of a base. Notice what the equation entails. Remember the square brackets, those are concentration brackets. So if we use this equation here to write this expression, watch what happens. It's the concentration of the products multiplied together divided by the concentration of the reactant. Notice that water is not included in either of these expressions, and it never will be, because there's no such thing. I shouldn't say there's no such thing. The concentration of a liquid is constant, and therefore it would not change from here to here, and therefore it would cancel out in this expression, and therefore you can't include it, or you don't need to include it. And the same would be over here. The same would be true. Since the concentration of a liquid is constant all the way through the reaction, it would cancel out with itself. Now, if these concentrations are really, really big and this concentration is really, really small, you can see that this number would be significantly greater than 1. Same over here. If these numbers were significantly big and this number was significantly small, this number would be significantly bigger than 1. And that's what we see. With strong acids and bases, their equilibrium constants, in fact, can't be measured, because what happens to this as this number approaches 0, this number is going to approach infinity. As this number approaches 0, this number approaches infinity. Now, you can't even do that on your calculators. If you take 10 times 10 divided by 0, you're going to get invalid error, right? Because you can't divide by 0. But as that number approaches 0, gets smaller and smaller and smaller, this number is going to get bigger and bigger and bigger, and that's what the point is. Okay, for weak acids and weak bases, that's not true. Let's see why. Weak acids and bases, there's a couple of things I want to point out. First of all, let's take a look at the picture here. We have our initial concentration of acid here before the dissociation and then after. Notice that we are not getting a very high percent of ionization, or, if you prefer, dissociation. Percent dissociation, ionization, those terms are interchangeable in this context. However, our initial concentration of the acid has only decreased by a small amount, and the same would be true of the base. So notice, we have our expression here. Notice we use a slightly different arrow. It's an equilibrium arrow. The other reactions went all the way through to completion. These reactions will not go all the way to completion. They will reach an equilibrium. So we use equilibrium arrows to represent that. Now notice here, for a weak acid, the Ka, if we take into account all of this, notice that the amounts of these are very small and the amount of this is still relatively large, is going to be less than 1. The smaller these numbers are and the bigger this number is, the smaller this is going to get. Same over here. The smaller this number is for Ka and Kb, the smaller that number is, the weaker the acid and base is. Make sure you write that down, right? Whatever the number is, the bigger the number is here, the stronger the acid. The smaller the number, the weaker the acid. The bigger the number is here, the stronger the base. The smaller the number, the weaker the base. Let's take a look now at some weak acids. Here is a list from the Chang textbook again of some weak acids. You do not have to memorize these. Any acid, and this is something you should write down, any acid that is not a strong acid, of the 7 that I had you memorize already, any acid that is not one of the 7 that I had you memorize is automatically a weak acid. Now look at the numbers on this picture here. Notice 10 to the negative 4, 10 to the negative 4, 10 to the negative 5, 10 to the negative 10. So you can see there's varying ranges of strengths. Hydrofluoric acid is much stronger than phenol, as you can see here. 10 to the negative 4 is a lot bigger number than 10 to the negative 10. Okay? Again, you don't have to memorize these or the Ka values. You just need to know how to use them when it comes time. And one of the ways you can use them is to determine how strong an acid is compared to another acid. These are the weak bases. Notice there's a theme here. The theme is that most of these bases contain nitrogen. Nitrogen is a compound, is a chemical as part of a compound that tends to accept protons, which makes it, of course, a Bronsted-Lowry base. Again, you don't have to memorize these, but look at the Kb's. Stronger to weaker. The values, same pattern that you saw with the acids. The higher the number, the stronger the base. The lower the number, the weaker the base. That in a nutshell is strong acids, strong bases, and weak bases. Here are the references for my lesson. Bring your questions to class.